Okay, my name is Dana Jacobsen. I'm going to be talking about Userspace entropy, or how you too can dabble in voodoo. If you'd like to ask short questions, I'll take them. I'll do longer questions after, and I'm here all conference, and I love talking about this. I will talk about it until you get very tired, but I also love learning about it. So first, I'll make this distinction between randomness and entropy. Randomness is a statistical property. So for instance, if you assume the digits of pi are normal, which we don't have actually proven, but if you assume that, they sure act like it, you could say, oh, the digits of pi are very random. But there's no entropy there. Entropy is this physical process of unpredictability. And so usually from a physical process, computers generally cannot do this because they're all very deterministic. But you can use physical processes to do it. So the right way to get entropy is using a hardware device. There are some available under $50. There are certainly many of them available for more. They use, for instance, atomic decay, or that's actually rather expensive, but you could do it with ADCs, video, all sorts of things. You can get hardware entropy. Or you could do it in the operating system. Sometime in the late 90s, everyone realized the operating system was the right place to put this, and they made devrandom in Linux. There are various other sources, and now newer Linux kernels will actually find your hardware and start reading from that to supply more randomness to its process. So some of the problems we get with this, maybe you have an old operating system, or you're doing an experimental operating system, so you don't have devrandom, you don't have these devices, or you don't trust it. GNU PG on Windows says, this is nice that Microsoft is supplying this wonderful method, but I don't trust Microsoft, or at least they're closed source, I don't know what to do, I'll do it all myself. So you're trading off one set of problems for another. Or maybe it's slow. It's, especially if you are on a virtual machine or an isolated server, it can be extremely slow. So I'll tell you a little story. In about 2005, I bought this Linksys NSLU2 network attached storage device, also called the Slug. It had 32 meg of RAM, ran a very underclocked ARM processor, and anyway, worked for a while. And at some point, I found CPAN testers and thought, this is really cool. I love CPAN testers, but it runs, almost everybody is running Linux, sometimes a BSD, on x86. So we're all testing the same thing. So I thought, well, this is certainly different. It's running some odd Arch Linux on a machine that almost nobody else is running. This will provide a nice source of testing. So I started it up, put it in a corner. It's using 10 watts or less, and it's very slowly going through CPAN testing. And at some point, I looked and said, wait a second, it hasn't submitted a result in over a week. What's going on? So I log on. It's doing just fine, but it's running an OpenSSH test. And that test wanted to read 4,096 bits from devrandom and then repeat that process numerous times. So here's a device with no hard disk. It's a USB stick. It's got no keyboard. It's got no mouse. It's on a switch. Nobody's logged in, so there's no network traffic. It's running 32 meg, I stripped everything I possibly could out of that. So there's no extraneous processes. And the poor thing, just, the kernel is saying, well, I have no entropy source, so I'm just sit here and hope one will come along. So this is when I kind of discovered this idea of running other things that can generate entropy for it. Now, of course, a cheap solution to this is you just link dev-urandom to devrandom, and then it stops blocking. But that's a different problem. So if anybody knows me, you know I had to say primes in my talk somewhere. In my N3 module, I wanted to generate random primes. And of course, there are lots of functions to do that. To do that, well, I need random numbers. And David Oswald was working on this module called Bytes Random Secure, which had a perfect API for what I wanted. I certainly recommend it. But as usual, that just leads to another thing. Well, at some point, Bytes Random Secure uses a cryptographically secure pseudo-random number generator, and it wants to get a good seed. So how does it get a good seed? Well, that's different on every operating system. So I wrote a module called cryptRandomSeed, trying to give that idea of, look, I just want good randomness, go get it the appropriate way. So on Windows, it will use the crypto API. It'll try dev random, dev u random. There are lots of different options for how it works. Entropy gathering daemon, it'll look at a bunch of different places, but at some point, if it can't find any of these things, what does it do? It goes to software user space entropy. It has to make it up. So rather than put that in that module, it goes to another one. So historically, how do you get randomness if you can't get it from your operating system? We've used time, we've used process data, network, all of these different things. If you look at papers from the 90s, there are lots of papers that describe how you could tease out some entropy from these things. Time is generally a terrible idea. There are lots of attacks that have been done because you've taken your nice intractable problem and turned it into a very tractable one of discover which time they used in this very small 1 hour period or so. So unless you do a whole lot of modifications, time is a bad idea. If you're just doing simulations and you're not doing cryptography, then who cares? But that's not really what this is about. The whole thing is to get entropy. So these other things are very easy for the operating system. They're kind of hard for the user space. For instance, if I'm just a generic user and I've logged into this machine, hopefully I can not read keyboard strokes and all the mouse presses. So that's really hard for me to do, which is one reason why this all got moved into the operating system at some point. But one thing I can look at is operating system timers. I can use SIG-alarm, I can use microsleep, and a high-resolution time. If I'm on a real-time operating system, a very good real-time operating system, if I ask to sleep 13 microseconds, I'll probably get something very close. I won't necessarily get 13 microseconds. But if I'm on a standard operating system, like most of us use, I won't get anything close to 13 microseconds. Maybe I'll get something kind of close. But every time I run it, I'm going to get something somewhat different. We have other processes going on. We have timers. The timers are not necessarily synchronized with the CPU. You've got scheduler jitter, a number of other things. So when I mentioned, cover a couple things in here. When I mentioned this idea, for instance, atomic decay, well, this is great. This is a wonderful source of randomness. Every time my little Geiger counter reads something, it puts a 1 in there, otherwise it's putting zeros. But I have this huge string then of zeros with an occasional 1. Well, that doesn't look random. 0 occurs far more often. So von Neumann looked at this quite a long time ago, and he said, well, we could solve this by looking at pairs. And if you see 0, 0 or 1, 1, we just toss it. If you see 0, 1 or 1, 0, then we'll output the first bit. And if you turn this long string of zeros with an occasional 1 into what actually comes out as half zeros, half 1s. This doesn't necessarily pass all of your statistical tests yet, but it's certainly a first step in getting that compacted. So we also want to do some sort of stirring or mixing process in all of this. And it turns out cryptographic hashes are very, very good at this. In fact, they have competitions to decide cryptographic hashes. They measure what's called diffusion very carefully to see that things that occur later in your original input do not just show up in the last bits or the first bits or whatever. They actually get diffused through the whole process. And there are different ways to do this, but they get tested very well, and that's one of the properties they have. So it turns out, I didn't know this, but Math Truly Random is a module on CPAN since 1996, one of the very early modules. And it does, it's actually mentioned in the Perl core documentation. You should use Math Truly Random if you want good entropy. It uses the TrueRand 1.1 algorithm from Blaze and Mitchell, who did it at AT&T in '95. And it uses this idea of operating system timers. So we set a short alarm, we run a busy loop, and then when the alarm goes off, we mix in whatever count we got in our busy loop. We do that 11 times. So this takes a while and keeps the CPU nicely humming along for a while. There's problems with this. It turns out there's not enough entropy in your output. You will get, at most, 8 bits of entropy out of every 32 you ask for. So that's not good. The mixing function is a very standard, what all of us would do if we're sitting down and writing C and we think, well, I've got to write a mixing function right away. XOR and shift, that's good. But it turns out it's not good. And it's very slow. So a year later, the authors actually published an update to this algorithm where they did 8 times more rounds. And they found this thing that NIST was working on called a cryptographic hash And so they used a beta version of SHA-1, which turns out it's exactly equal to SHA-1. So that fixes those problems, but since it does 8 times more rounds, it's actually slower. There's a problem with the implementation of math truly random, however. You run it on Windows and you get all these compiler errors. Oh, you can't use Cygalarm on Windows. You run it on Linux and tests hang forever. So that's not good. The last time it had an actual pass was in 2008 on a Solaris box. I believe it's had 27 passes total since 1996. So I supplied a patch, wrote something in pure Perl in January 2013, but the maintainer died over 10 years ago. So unfortunately, we can't, no one can apply that patch. So I did request that we either deprecate or I could adopt that module because I have a patch that makes it work on these systems. So the author, if you remember, TrueRand was written by Blaze and Mitchell, and that's what Math Truly Random uses, he heard someone was looking at this and wrote the following tweet in 2012. And he said, voodoo entropy had its place, but this belongs in the operating system. Now, one of the, I don't know if it's a motto of Perl, but maybe it is, certainly a motto of most of us here, fun is more important than you shouldn't do this. So I thought this was a lot of fun, and it had a purpose. So I wrote this thing called timer entropy using SHA-2, trying to come up with a catchy name, so it was Tesha-2. I wrote it in 2013, had never heard of Math Truly Random, but I had heard of this timer entropy daemon, and so I got the idea from that. So it's in pure Perl, uses 2 modules that are in core at 5.10 and later, runs on Linux, runs on Windows. It was actually very easy to write because of modules that are already on CPAN and are in core. So internally, it uses a very similar process, but without the busy loop. We get time of day, we sleep a little bit, get time of day again, and then XOR the actual delay with what we expected. You could also subtract. And then repeat that 8 times, and then SHA-256 the whole thing. So that's the internal, but it uses a concept of entropy pools. So when you actually call the routine, you're going through an entropy pool, which is a very standard concept. DevRandom uses it. Yarrow and Fortuna use entropy pools. If you look up cryptography books, you can usually find discussions of entropy pools. So the idea is adding to it. In my case, I'm using SHA-512 to mix. You take the pool, you concatenate the entropy you got through using that internal routine, and you stir it using SHA-512. So to extract, we add entropy as needed. This is where DevRandom would block, waiting for entropy. In my case, I can just keep calling that routine. It generates entropy. And then SHA-512, a counter plus the pool is what I'm going to return, which is kind of important that you don't want to give people the pool that you're using because then they could see your internal state. So one of the things you do is basically you pour some out, put something in it, stir it up, and give that to them. And you may have to repeat that. So another way of looking at it, if you need to, pour in some entropy and stir, pour some out, add a counter, stir it out, output it, repeat as needed. Because I have a 512-bit entropy pool, you could ask for 4,096 bits, so I have to keep moving along through that. So this passes various statistical tests like ENT, Test U01, and Die Hard. Math Truly Random does not pass those tests, which we expect because TrueRand 1.1, we knew didn't do that. Timer entropy D does not pass those. However, if you're using timer entropy D to put into a modern Linux kernel to supply it randomness, it will churn through a lot of this stuff. The kernel is very good about taking all sorts of different sources and making the best use it can out of them. So how much entropy does this process generate? An interesting thing was to test and configure this at compile time. So actually measure how good are the timers at compile time, how much entropy do we think we're getting, and then configure that. So how many times do I have to call that random byte routine to actually get enough entropy? And I try to be conservative. All of these algorithms always try to be conservative. So anything over 8 bits per byte is certainly good enough. I'm estimating it at 21, estimating it at 32 plus for Windows. There's this problem, of course, is that if you measure once and you run it later, how do you know you're getting the same thing? One possibility is measure it dynamically, so every time you go get some entropy, go measure some more. That can cause it to be extremely, extremely slow.
I apologize, I don't know much about the mathematics behind entropy generation or anything, but can you explain to me what you mean by 21 bits per byte?
So I've estimated that every time I call this random byte routine, it's returning 21 bits of entropy.
Can you explain to me how it can have more than 8 bits worth of entropy? Or is that something that's coming out?
I'm being so we've estimated that there are 21 bits in this whole process.
My question is like, how is it not, I mean, I'm sure it is, but like, how is it not mathematically, like, the ceiling of entropy is the number of bits?
The ceiling absolutely would be 8. So another way of measuring it is if you took a byte, well, a string of bytes, and you tried to compress it using an ideal compressor, you'd get no compression. As your entropy falls below 8 bits per byte, you would get compression.
Is it 21 bits of your stream or 8 bits of output?
For 8 bits of output, we've estimated that there were 21 entropy bits that went into making it, which is more than enough.
But not 21 bits of true entropy because you only have 8.
We're not actually getting 21 out of that, of course. So this is kind of confusing in the sense, because actually it's returning, that internal call is actually returning 256
This is really how
bits.
much of your supposed entropy you're using.
This is how conservative I'm being with this. It's confusing. Overkill is another way of looking at it. Yes?
Another question on that. So I think I understand what you're saying, but is there a sense that by taking those bits out of the entropy pool, the pool needs more entropy back, or is it?
So this is, every time I want to put 8 bits in, I estimate that I'm actually putting 21 in. So we're supplying it far more entropy, we think, than we really need to.
Okay.
And then we take out, if you wanted however many bits, we take out 256 bits. But that means we thought we took 256 out, so we'll have to add 256 more. We're estimating we're actually adding a lot more. So it's slower than it has to be because I'm trying to be conservative.
I see. Okay, thank you.
Yeah. So how fast does it run? It varies greatly depending on your operating system and your timers, and it doesn't vary so much based on what's going on the machine in most cases. Again, if you had an isolated server, maybe a little different, but I've run it on isolated servers. It runs fine. Varies 230 kilobits per second is approaching the speed of a lot of those hardware devices. Most machines are not running that fast. Cygwin on this little atom runs at 60 bits per second. On Windows on the same machine, it was getting about 17,000. An old HP Xbox was generating 20 bits per second. It was very, very slow.
What accounts for the factor of 20 between Linux and Windows?
I believe it's the timer, the amount. The closer you can get to the actual, if you say, I want to sleep 27 microseconds, and you come back with 27 plus a little tiny bit, that little tiny bit is what we're getting as our jitter.
So because Linux is closer to real time?
Linux is getting you your sleep more accurately.
It has better timers, therefore worse entropy.
Yeah. Yes.
Or couldn't that be Linux has the clock rate at which it tests switches?
Your clock rates differ, yeah.
So that's a configurable kernel parameter. Maybe it would be interesting to see what different settings of that would have.
Yes.
better clock rate.
Yeah, there are a lot of things that would go into it. If your scheduler comes back to you right away, then you won't spend extra time in that process. So arguably you could say Linux is worse because it's waiting longer sometimes.
But like one of the settings, I think you can set that parameter for, they recommend like 300 hertz for servers and 1,000 hertz for desktops or something.
Yes, yeah, I remember that.
So
how do you use this again to help your original problem where you have some external program that's presumably still looking at that random, right?
Okay, so if you wanted to use it for that, you would run this and you would send it to the kernel as here's a source of entropy, and I can use that.
That is something you can do.
And that is something you can do, though I would say there are people who have spent a lot of time on this. Have GED for daemon is something people have worked a lot on, and they do this plus a whole bunch of other things, and that will just sit there and run and poke data into the kernel.
The other thing I thought at the beginning is it would have been a crazy bug is he must have done this too, by logging, by SSHing in, you may have provided enough entropy.
Oh, I did, yeah. As soon as I start typing, it starts immediately, you can actually look at how much entropy is in the kernel pool, and as you start typing furiously, it will generate more, yeah.
Where's the problem?
Yeah, fortunately it hadn't done that much. So, very quickly, we can ask, how do you test this? Testing these things is always very hard. One of the things is, if you don't have good enough timers, you really can't use this properly. So there are some devices that just quantize, or operating systems that quantize all of their returns, so you don't have microsecond timers, and therefore, at install time, this would decide you can't use it. I also wrote FIPS 140. We do some, doing the test process. It does the measurements again of what it thinks it's getting. So in conclusion, this was a lot of fun. It can be useful. I think it was under 90 lines. If you strip out all the comments are probably 5-6 times more than the actual code. It's under 90 lines because of the wonderful modules from CPAN. But maybe you should just use your operating system. That's it.